Hello everyone. In this lesson, we are going to study about addition reaction, mainly addition of metal hydride to carbon heteroatom multiple bonds. Content, we will cover metal hydride reduction of carbonyl compound, unsaturated carbonyl compound, carboxylic acid, ester, and nitrile. Reduction of carbonyl compound. Carbonyl compounds gives variety of useful derivatives. You are already familiar that they mostly undergo nucleophilic addition reactions, in which a nucleophile is first attached to the carbonyl carbon, followed by a proton, usually taken, and that's how the addition to the carbonyl bond take place. So, in the carbonyl group, the oxygen atom is electronegative, and this results in the carbon-oxygen double bond polarization. Due to this polarized nature of the carbonyl group, it is very reactive, and it will be easily attached by the nucleophilic species. So, the electrophilic carbon atom of the carbonyl group is, as you can see here, it is sp2 hybridized and flat, and this makes it relatively unhindered and open to attack from either up and down side of the double bond. Reduction with sodium hydride. A negatively charged atom like hydride ion can act both as nucleophile and as a base. Whether a hydride ion, H-, will act as a nucleophile or a base, depends on the reagent used. Let us consider the H-, which is generating from the metal hydrides called sodium hydride. Sodium hydride is an ionic compound. Hydrogen from sodium hydride is very small in size and has high charge density. It only reacts as a base and not as a nucleophile. This is because the contribution of hydrogen atom to the sigma star orbitals of the HX bond, where X is any atom, is ideal for interaction. Instead of this, 1s orbital is very small to link with carbon's more diffuse 2p orbital contribution to the lowest unoccupied molecular orbital, pi star, of the carbonyl group. So, adding H- to the carbon atom of a carbonyl group would yield an alcohol, and shall be a very helpful reaction. But, the carbonyl reduction to alcohol cannot be done with sodium hydride. So, what can be added to achieve this? The simplest answer is NaBH4, or lithium aluminium hydride. Now we study the reduction with NaBH4. It is a water-soluble salt that contains tetrahedral BH4- anion, which is isoelectronic with methane, and there is a negative charge on BH4-. This is because boron contains one proton, less than the carbon in the nucleus. Though no hydride ion, H- is actually involved in the reaction, the transfer of an atom of hydrogen, with an attached electrons pairs, can be regarded as a hydride transfer. In other words, from BH4-, one of the hydrogen, with the electron pair, is getting transferred to carbonyl carbon. Note that it is the hydrogen atom that forms the new bond to the carbon. This reaction may be illustrated with a curly arrow as shown here. The oxyanion produced in the initial step helps in stabilizing the electron deficient BH3 molecule by adding to its empty p orbital. As a result, a tetravalent boron anion is produced again, which in turn transfers a second hydrogen atom, with its pair of electrons, to another molecule of aldehyde. This process can continue, in principle, so that all 4 atoms of hydrogen could be transferred to molecules of aldehyde, one by one. But in practice, all the 4 atoms of hydrogen are not actually transferred. The first step is carried out in the presence of ethereal solvents, like THF and diethyl ether. The water, or alcohol, added in subsequent step, to work up the reaction, and this is from where the proton from the solvent, for the alkoxide ion to take this proton, and get it converted into alcohol in the last step. Sodium borohydride reduces both aldehydes and ketones, though the reaction with ketones is slower. For example, as you can see here, benzaldehyde is reduced about 400 times faster than acetophenone in isopropanol as solvent. Sodium borohydride is one of the weakest hydride donors available. In fact, almost no reaction with water is evidence of this, else it would have combined with water, just like Na, where H- would have acted as base. Talking about specificity, sodium borohydride is a specific reagent, and does not attack the carbon-carbon double bond, or triple bonds of alkenes and alkynes, respectively, as they are not sufficiently polarized. If multifunctional groups are there, like carbonyl, alkene, and ester etc., in a molecule, carbonyl group reduces aldehyde and ketone functional groups only, and don't have effect on double or triple bond of alkene and alkyne. For example, look at the second reaction. In this molecule, which having ketone, alkene, and ester group, only ketonic group is getting reduced to corresponding alcoholic group. The carbon-carbon double bonds, as well as the ester functional groups, are unaffected. Reduction with lithium aluminium hydride. Lithium aluminium hydride is a strong hydride donor reducing agent, and it has the tendency to combines rapidly with water. It is more electropositive than boron in sodium borohydride, and this is the reason why the hydride from lithium aluminium hydride is more electron-rich, and thus is a stronger base in reaction with water, and also stronger nucleophile when reacted with functional group like carbonyl group. Let us look at both the action. First one is basic action. In the basic action, lithium aluminium hydride reacts violently and dangerously with water in an exothermic reaction that produces highly flammable hydrogen. And similar reaction will take place with milder groups like carboxylic acid, as you can see here, equation showing how lithium aluminium hydride reacting with carboxylic acid. Coming to the nucleophilic action. In its nucleophilic action of hydride, lithium aluminium hydride reduces all type of carbonyl groups, like aldehyde, ketones, esters, carboxylic acids, and amides. Aldehydes and ketones are reduced to primary and secondary alcohols, respectively. If you try to understand the mechanism of reduction of lithium aluminium hydride, you can clearly see here that from AlH4-, the hydrogen will be transferred as H- to the carbonyl carbon, and a result, we have this alkoxide attached to aluminium, with another mole of aldehyde, it will be giving you this particular species, and finally after hydrolysis, there will be formation of this corresponding alcohol, from alkoxide part, that is, RCH2O-, get converted into RCH2OH. Reduction of unsaturated carbonyl compounds. What happens when the reducing agents, especially hydride reducing agents, are subjected to carbonyl compounds? You are already aware that the stability of conjugated dienes is higher than the non-conjugated dienes, and this is due to delocalization of charge through resonance. Let us understand how the presence of conjugation changes the reactivity of unsaturated carbonyl compounds towards reduction by metal hydrides. A carbonyl group shows nucleophilic addition reactions at carbonyl carbon, but when you look at the example shown here, unsaturated carbonyl compound give the following product, and they are the products of addition, not to the carbonyl group, but to the CC double bond. This is known as conjugate addition, or direct addition to the carbonyl group. Reduction with LiAlH4. If you consider the reduction of benzyl acetone, that can lead to either the allylic alcohol, via normal 1,2 addition of hydride to the carbonyl, or it can leads to the saturated alcohol, as shown here, via 1,4 reduction. Reduction with NaBH4. Sodium borohydride reduces alpha-beta unsaturated aldehydes and ketones to saturated alcohols. The borohydride has reduced not only the carbonyl group, if you notice here, but the double bond as well. In fact, the double bond is reduced first in a conjugate addition, followed by addition to the carbonyl group, as you can see here. See the mechanism here, the cyclopentanone, through conjugate addition, first the double bond is getting reduced, and then the second addition is happening to the carbonyl, and then the carbonyl is getting reduced to the corresponding alcohol. Reduction of carboxylic acids. It can be done in variety of manner. So first of all, we will see the reduction of carboxylic acid with lithium aluminium hydride. Carboxylic acids are easily reduced to primary alcohols by the help of lithium aluminium hydride. The reaction here goes via the intermediate stage of aldehyde, but it will not stop at aldehyde stage. It cannot be isolated because it is more reactive than the original carboxylic acid. Further, it will give rise to the corresponding alcohols. If you talk about conditions, the conditions required are particularly mild, and the reduction proceeds quite well at normal temperature. See the reaction. Here the carboxylic acid is getting reduced to particular corresponding alcohols in excellent yield. Reduction with lithium aluminium tertiary butazine hydride. Reduction of carboxylic acids to the aldehyde stage is difficult because aldehydes are more reactive than carboxylic acids towards most reducing agents. Almost all reagent, which converts acids to aldehydes, will also reduces aldehydes to primary alcohols. This can be achieved if we take weak reducing agent, for example, lithium aluminium tertiary butazine hydride, which is a weaker reducing agent, as compared to lithium aluminium hydride. Acid chlorides are strong activators for the nucleophilic addition, due to -I effect of Cl. Hence, it will converts acid chlorides to aldehydes, without further reduction to alcohol. In these conditions, the aldehyde reduces more slowly, and can be easily isolated, without the problem of getting converted into further alcohol. Let us understand this with the help of example, as you can see here. This is the isobutyric acid. First of all, with the help of SOCl2, it get converted into corresponding COCl. And then, with lithium aluminium tertiary butazine hydride, the COCl get reduced to isobutyraldehyde. If you look at the mechanism, acid reduction to an aldehyde is a two-step process. The first step is the conversion of the acid to the acid chloride. And the second step is the reduction of acid chloride using lithium aluminium tert butazine hydride into the corresponding aldehyde. Reduction of esters. For unsaturated esters, conjugate addition occurs, and there is also a significant role of steric hindrance. If the beta carbon of a carbonyl compound is more hindered, the nucleophile is less likely to attack there. But there are several nucleophiles that can undergo conjugate addition, even at such highly substituted carbon atoms. For example, you can see this particular reaction, where the reduction of ester using sodium borohydride will give you the particular product, that is, alcohol. Esters can be reduced to primary alcohols using lithium aluminium hydride. When lithium aluminium hydride is used as the source of H- to attack as nucleophile on esters, the esters get reduced to alcohols. Reduction of nitriles. Lithium aluminium hydride is a very strong reducing agent, and this is used to reduce nitriles. In case of nitriles, the carbon of the carbon-nitrogen triple bond acts as electrophilic center, where the hydride is attached, and this is because the nitrogen being electronegative, hence, the carbon is electron deficient. So, the hydride adds twice to the nitriles, due to the triple bond, and during the reaction, aluminium complex basically act as giant proton, for example, Lewis acid. Here, you can see the mechanism. From starting with nitriles, how the hydride will be transferred from AlH4- complex to the carbon, giving you C double bond N-, and another hydride transferred to the C double bond N to the carbon, giving the particular species, which further on hydrolysis give particular amine. Thank you.